Hi everyone, welcome to my video series. In this video what I'm going to talk about is free fall. So at this point we talked about 1D motion, we talked about constant speed, we talked about acceleration. Now we're going to talk about a particular type of acceleration and a particular type of 1D motion, the motion that moves vertically. So we're going to restrict our motion, like I said, to just up and down. I know in a couple of diagrams they're going to look like this, just so I'm not drawing on top of myself in terms of modeling the motion, but just know we're restricted to up and down right now. We will do this motion next, so stay tuned for that. So we're going to talk about things that are in free fall. I'm going to talk a lot about what are the conditions of free fall. We're going to talk about the all the characteristics of free fall. I'm reading my slides. Time, position, acceleration, all that fun stuff. And then, of course, I'm going to save the next video for all the problem solving. So I think it's good to have concepts and then problem solving in two separate videos like that. So yeah, here, let's start this. Oh, okay. So this is a demonstration I do. So I'm going to do it for you at my house at night. So hopefully my kids don't wake up. I can only do it once, because otherwise they might wake up. So this is a typical demonstration I do in class. Let me move this out of the way. And I hope I'm in the frame because it doesn't show me my own video. Fun fact. So this is a demonstration I like to do, which hits the ground first. So I have a piece of paper, right? And I have a book. Now I purposely picked a light book because, like I said, I don't want to wake up my kids. And it's actually my music book. And just to prevent all my music from falling out, I'm going to go ahead and do that for now. So the point is, or at least, you know, as you can see, the paper in the book, well, it doesn't matter. Anyway, I'm going to hold them at the same height and I'm going to drop them at the same time. So I'm going to have you predict, of course I am, which one hits the ground first. So here's my quiz question on that. Okay. I will probably read your quiz anyway, but I assume most of you predicted that the book would hit first, right? So I'm not going to explain it just yet, but I am going to change it up. So now instead of taking the paper right here and doing it side by side, what's going to happen if I do this instead? So let's make a quick little assumption before I do that. A lot of times people assume, you know, that, well, not assume, it's true, that this is a lighter mass than this. As you might imagine, the book is heavier than this. So this is a heavier object, so it falls, as you can see, faster than this light object, right? So what happens if I put the light object and the heavy object together? Would it do what it just did? The heavy object falls faster, so this would go first, then the paper. Does the paper and the book go together? Does the paper lift up first, then go down? Or does this paper go underneath this and fall, and then this falls afterwards? So a couple choices. Once again, I will quiz you on this, so select your value now, and then I'll do the demonstration. Okay. Ready? Let's see what's going to happen. Husband's gonna think I'm dying. So notice the difference, right? I promise I won't do it again because, like I said, I don't want to wake up my children. So notice what happens here. In this case, they fell together, right? So, you know, again, I would do this in class and I'd ask for volunteers. So, you know, we talk about this. So, unfortunately, I don't have that dynamic. If you know right away and can beat me to it, you can put it in the comments section. That'd be pretty fun. But anyway, let me describe what's happening here. The paper has a lot of air resistance, right? In fact, you can see this kind of floaty, oh, that came out really good, right? This kind of floaty effect with that. And what happens is when I put the paper on top of the book, it blocks the air resistance. And this proves a very interesting point, that if air resistance is blocked, objects will all fall at the same rate. So in other words, the mass doesn't actually matter. If it did, we would have saw the book go first and then the paper. That would have proved the point. So this was a very keen observation by our friend over here in the slide called Galileo. And, it's, without thinking about it too much, I mean, the observation is here. The heavier object does hit first. But he was smart in that he questioned that. And he said, well, is that true? How does gravity know to pull that one harder than this one? He was asking these pretty deep questions. So he did another experiment. 2 ordinary pieces of paper, right? They're both the same mass. So watch what happens when I take this and I crumble it up, right? This is still the same mass. I changed its shape, so its volume's different, but this is the same mass as this. Watch what happens now. Pretty cool, huh? First time I saw that, I was like, wow, that's really cool. How did that do that? This ball of paper falls just like a book, and I would do this in class, but like I said, I told you I'm not going to wake up my children. But don't ask me why I have this in here. Well, the answer is because I have children, and this is what they do. They just bring things. And this is funny that it's toilet paper in this interesting times that we have. But anyway, the point I wanted to show you is that they fall together, right? I chose that because it doesn't actually make a loud noise when it falls. And another fun, silly fact is this toilet paper will come back to physics. I have to talk about its other motion called its rotation, which toilet papers are really good at. Right? Silly things. Anyway, the point is, I feel like I have to sit for this. Okay, the point is, hopefully I'm back in the camera, is that it's not about the mass of the object. And in fact, the main point of this demonstration is to show you, in the absence of air resistance, all objects fall at the same rate. This rate's called the acceleration due to gravity, so things get faster, which is interesting. So the longer they fall, the faster they go. And that rate's the same regardless of the mass of the objects. So here's some pretty cool YouTube videos that show these things. So if you're not familiar with Brian Cox, I know most of the celebrity physicists. He's famous on BBC and all that fun stuff. So let's go ahead and play this video. We're going to do video inception, right? We're going to video this video. Now this is a really cool video because it shows you that a bowling ball and a feather will actually fall together in a vacuum. Hopefully this will work. Now what makes this extraordinary is that they do this in NASA's vacuum chamber that they use to test spacecraft. So this is like epic, this is like stories tall, like very, very high. And they take this and they of course release it at the same time. Last time I tried to do this, it did this to me, so I'm not too surprised that it's doing this. I don't even know what that's down there, and I don't even look at it. So, let's try a new link. Let's do, what is that, bowling ball and feather. Drop at the same time. Let's see if I can just get a different video. Oh, good, the shortened one. Hopefully this works. One of these has got to work. Let's try this. I'm stubborn, so I got to do it until it works. All right, here we go. So this is Brian Cox.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space.
Okay, so now they're going to drop it. So we're going to go, okay, it's coming up soon. Okay, so this is in regular air. Notice he's standing there, so he's breathing, so there is air resistance here. There we go. Alright, let's get to the moment of truth. Right here.
7, 6, 5, 4, cameras on, 2, 1, release.
I've seen this 100 times. It's still really cool. Look at that.
Exactly.
Even the NASA scientists are surprised.
Exactly the same.
Isn't that so cool?
Look.
I had to like pause, like I had to like not talk during that. Did you notice that? So such a cool thing. I love that video, and I highly recommend you watch it. Brian Cox does a lot of particle field theory, so he's very famous for like string theory and all that stuff. He's wrote many books, so he's, like I said, he's a physics celebrity. So they did this too on the moon. So the
Well, in my
quality, of
left
course, is
hand I have
terrible.
a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Isn't that cool?
Which proves that Mr. Galileo was correct in his findings.
Okay, so as you can see, sorry, this isn't a slideshow. My title's gone. But as you can see, if they're in a vacuum, so let me define that too, because sometimes you might see that in physics problems. The word vacuum means no air resistance or no air, so just be aware of that. So if there is air resistance, like we are existing right now with air, you won't see this effect because the air can actually push back on objects. And then causes their speeds to change. So I think I do talk a little bit about that in forces, but that's what happens. But in the absence of air resistance, that's important. Sometimes this is modeled as drag if you're doing engineering. My husband's an engineer, so we would do. We went to college together too. It was silly stories. But anyway, we would learn the same thing, but he'd call it one thing and I'd call it the other. So I'd be like, oh, I'm doing my air resistance problem. He's like, your drag problem. I'm like, nope, we call it air resistance, we call it air drag, so it's just like, some terminology issues. But anyway, the acceleration of the object is constant, and it's at a value of about 9.81 meters per second squared. Now, that number doesn't just come out of nowhere, it's actually a property of the planet's gravitational pull. So every planet has its own gravitational G value. For example, the moon is 1.6. Here is almost 10. So if you notice the difference, the size does change the value of the gravitational acceleration. Some other common examples is Mars is 3.72 meters per second squared, and Jupiter is 27. So as you notice, the size of the planet directly affects the value of the acceleration due to gravity. When I do gravitation, I'll actually derive where this number comes from. And I say the mass, but there's actually radius that has to do with it and some other features. It's a vector. Acceleration is a vector, and the acceleration is pointed toward the center of the object, which is the Earth. So we just model it as downward, okay? So we use G often to model motion. As you see, I have a list of places where G is used. But during this unit of linear motion, it's vital that you model it with the vector nature, which is negative. Now, when we do forces, we'll model the force negative, not G negatives, but it will be downward anyway. So the rest of the time, we're going to actually just use the magnitude of the value. So remember, magnitude means just the value, so 9.81. Right now, you can memorize that in linear motion, the acceleration due to gravity is negative 9.81, modeling the downward nature toward Earth. So, when it comes to defining objects in free fall, we talk about things that are under the influence of gravity only with no air resistance. So I'll tell you right off the bat that all the questions that you're solving, unless they otherwise specify, you can assume no air resistance. There are some that do ask about air resistance, but you can assume that, we're not going to model it. Turns out the models without air resistance are pretty accurate for the most part. In other words, if I were to drop this tape measure from here to here, considering air resistance, it's like 0.0001 off or something like that. Now, the farther and longer it falls, the more air resistance you do have. So it does build up, and the faster you move. You know that because you've ever done this in the, I don't know if you can see my video, but if you've ever done this in the car, right? Your hand moves up and down, but only when you move fast. If you're moving slow, it doesn't move. It needs to have lots of air build up. This is Bernoulli's principle, which unfortunately we don't talk about, why you get lift when it comes to doing that. But there is air resistance. Another quick demonstration is move your hand very slow or move it fast. You only feel the air when you move fast. So go ahead and do it. Nobody's going to see you. Maybe some of your family members, but it's okay. They're fine with you anyway, right? But you can feel, or, if you're running or you're going really fast, you can definitely, feel the air resistance. Okay, enough about that. So, I'm actually going to skip down to the part where it says objects that do not model free fall. So free fall is under the influence of gravity. So that paper example that I showed you, I don't have any paper, I have a small paper here. So that does not model free fall because there's significant air resistance. Paper, coffee filter, feather. Two other fun facts. Snow doesn't actually, is very light. So when it falls at a constant speed. That's called terminal velocity. So snow is not free fall because there's significant air resistance. And rain too, fun fact. Rain has a lot of air resistance on it. In fact, it's because of the air resistance that rain doesn't actually hurt us when it falls. It falls really far. I think I've done a question on that before. Like how fast would a raindrop go if there wasn't any air resistance? I think it's like crazy, like 1,000 meters per second, like that. It's pretty wild. But anyway, terminal velocity. It just means that you might have heard that when you have skydivers, for example. That happens when you're falling. You're falling downward with gravity, but the air pushes up with the same force. So you need to be moving fast and for a while for that to happen. So like a skydiver is a great example. As the person's going down, the air pushes back up with the same force. And if the force down and the force up cancel out, they move at a constant speed. So they don't accelerate. That's the key part, is they don't accelerate. And things that actually add forces or push with propulsion, like airplanes and rockets. So those are all examples. Flash forward to your exam, going to ask you a question, which of the following model, free fall, like that. So other things that model free fall. So I think most of you are comfortable with the fact that this example, taking an object and dropping it, is free fall. People are not comfortable with the fact that this is also free fall if I throw it. Now, the reason why it's free fall, now it's only free fall when I let it go, even when I throw it. Because when I throw it, after the card leaves my hand, like that, the only force that acts on it is gravity. So I do have to be careful. When I throw an object, not during the throwing part, but when I release the thrown object, it's now free fall. And that's true for up or down. And it's weird, if I throw this up, obviously this is a piece of paper. I'm holding this to see if I can move some things around here. That thing is going to shut off on me, I know it. I don't have a ball. I have I have a ball. Hold on. I have like a million balls because we bought one of those, kid ball pit things, and I have like 1,000 in my house, and I just find them everywhere, like in my office. There's no kids' toys. Well, that's not true either. But the point is, kids' toys are not stored in here, and here's that ball, right? Anyway, this is actually free fall because once it leaves my hand, that moment that it does this, it's under the influence of gravity only. You have to believe that this is true. I know you don't like it, but once it leaves my hand, the force is gone, and the only thing that's pulling it down is gravity. So thrown upward. And then this example, the 2D example. Now, with two-dimensional motion, we're not going to do that now, but that's technically without propulsion free fall. So what it means, so if I round this to about 10, which is a nicer number to think about, it means every second the speed increases by 10. So, within 5 seconds, instead of, you're going 50 meters per second. And just to give you that perspective in feet, it's actually 32 feet per second. So every second you move one full story of a building, and you increase a full story every second. So the first second you're moving one full story, the second is 2 stories, third second is 3 stories, etc. like that. So it's a pretty significant change. If you're falling for 5 seconds, that's a long time. So just think about that too. It's unlikely that you'll, unless you're a skydiver, you'll be falling for that long. Yeah, this is fine. Ooh, quiz time. Which one, you're going to see one just like it on your upcoming exam, so try it out yourself. So this will be a quiz question for you. See how you do on this. I'll wait for a second. All right, so I hope you notice that the best answer is, I have to look. Let's see, tissue, nope, tissue is not a good example. Significant air resistance, no is terminal velocity. Satellite being launched into orbit, that's propulsion. Electron revolving around an atom, that's a different type of force. And the answer is E, a dart thrown toward the board, sorry. And of course the reason for that is once the dart is gone, even though it has a forward motion, it's technically in free fall. Okay, so I want to model this object, and I want to talk about the time, acceleration, and velocity of the object. Now I must direct you to, let me go back, oops, sorry, to this motion. So first of all, I want to let you know that what I'm modeling is this case, the straight up and down of this object, just like that. But I made it into an arc so that you can see it better, so I'm not writing on top of myself like that. But it is, in fact, moving up and down. So imagine that it's doing this. So it turns out that this thing has symmetry. Symmetry. Come on, let's write. Nope. Nope, that's not what I wanted. Symmetry. Oh, I'm gonna pause my video for a quick second. Okay, I wanted to just clear that stuff so it wasn't in your notes here. Okay, so like I said, we're gonna do some symmetry. Symmetry, basically meaning that if I cut this in half, we'll have some common features on both these sides, right? Now, first of all, I want to talk about the motion of this ball, right? So, as this ball is rising, the velocity is going to be a positive value as it's going up. At the very top, the object stops momentarily. In fact, objects have to stop to change direction, right? So this at the very top, the velocity up here is going to be 0. It's not positive or negative, it's 0. And then from the top, as we go down, the velocity is going to be negative. So if I were to draw the object right here, the velocity vector would be pointing upward like this. There would be no velocity vector here because there's no velocity, so it would be missing. If I drew the object right here with the velocity vector, it would be straight down like this. Sorry that I'm going over, I just wanted to model the, you know what, I won't do as negative because I'm already accounting for the direction right here, but it would be down like this. The acceleration will always be negative because it's that due to gravity and it's constant. So the acceleration would be down here. The object up here, if I were to draw it, let's draw it in the colors that I have. If I drew the object up here, it would just have the acceleration. And this would be like this. So tying in something I talked about before, remember when these are opposite, this is a slowdown. And hopefully that makes sense. As this object rises, it slows down and it actually stops. And then since they're together, they actually speed up, right? Connections, right? And another weird thing is, yes, you can have an object that's not moving, but experiencing an acceleration. The acceleration at the top is not zero. It's a very, very common misconception. A lot of people get this exam multiple choice wrong. So just be careful with your vectors as you do it. So this will be, sorry, let's do that, 9.81 meters per second squared. The whole time. It's constant. So A is constant. And I wrote it as A here, which is fine if you wrote it as G as for our constant G. So G is, I didn't mention this before, it's like pi, you know, we know that pi is 3.14. This is the symbol for G, that number that's always the same kind of idea. Now I'm just going to make up a velocity. Let's make up a number. Let's make up 8. I like 8. So like I said, this actually has symmetry. So if you throw the object with 8 meters per second up, as long as you catch it in the same spot, it will also be 8 when you catch it. Notice that, actually, fun fact, this is actually not drawn at the same height. Let's add that in. So if we're at the same spot, in other words, you know, my hand won't actually stay in the same spot, but let's pretend that it does, right? I catch it and throw it with the same speed. Pretty neat, huh? So if you throw a baseball 90 miles per hour up, guess how fast you're going to catch it? 90 miles per hour when you catch it. So that's pretty fast, right? Ever catch a softball? Does anyone play softball or baseball? I remember one time I caught a baseball from like a fly and I was like, ow, that hurt. That stuff's hurt. I mean, that's why you wear glove, but still. I was surprised. But anyway, that is a helpful technique and trick when we solve problems. So if ball is, now the ball doesn't actually have to be caught, it just has to be at that position. If the ball is at the same position at which you catch it, the velocity will be the same. I like what I said, if the ball is at the same position of which you threw it, of which it was thrown, it will have the same, now notice my wording, speed, has the same speed, how fast it's going, but it would have a negative velocity because it's moving down. Pretty cool stuff. Another cool thing, let's use green. So imagine that my time is, so we'll put it at time 0. You know, at time 0, these are my initial conditions. Let's say it takes, I don't know, 3 seconds to get to the top. By the way, these numbers don't work. I'm just doing them for examples. If we were to calculate this, this is not true. I just want you to know that. The point I'm trying to make is if it takes 3 seconds up, then it's gonna take 3 seconds down. Oops, sorry. Yeah, okay. I'm gonna write it like this. 3 seconds So 3 seconds up, and this would be 3 seconds. I don't know why I wrote seconds. Down, which means the total time would be 6 seconds. So without even calculating the problem, if I knew the total time, I can say, oh, I know it takes 3 seconds to get to the top because I'm going to take this number and divide by 2. Super helpful. Super, 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 super helpful. I can't even express how helpful that is. Because when we want to look for things like maximum height or altitude, that happens halfway. But if I want the total time, maybe I only have the time for the max altitude. I can just double it. So it's just these simple tricks that are super helpful. So time up equal time down if and only if you have a symmetric problem like this. So if thrown up and catch in the same position. Now, I hope you do agree with me that it is true that if I were to take this object and throw it up and not catch it and let it keep going like that it definitely is not symmetric anymore, right? It's not going to, that speed at the floor that ball hit at is not going to be the same speed as what you would catch it with. It's going to be more. But these are really just helpful things when you're solving problems. So not all problem solving is plug and chug. Problem solving is about understanding the motion and using these little tricks of mathematics that I'm sharing with you to help you figure them out. Let's see. Let's do that. So I have this slide for you because they just do a really nice job of explaining the same concept in a nicer way. So notice that if you start with 20, you end with 20. Notice that if it takes 2 seconds up, it's 4 seconds down. Another cool thing, it doesn't have to be here. If I pick a random location, like right here, and I just know that it's 10 meters per second here, I'm at a height of 15, it's at 1 second. Well, notice that as long as the displacement's the same, the velocity is the same. Pretty neat, huh? Same thing, if it takes 1 second to go up, it'll take 1 second to go down, right? So 1 and 1 is 2, 2 and 1 is 3. Notice the velocity vectors that they're showing here. The speed slows down as you get to the top, but it speeds up. They're longer as we get to the bottom. So I wrote everything down that in the previous slide right here for very helpful problem-solving techniques. Ooh, and I think this is the last one before we do lots of problems. So what are the direction vectors of acceleration and velocity of an object being dropped? Oh, look at that. My animation's working. Yay, so it's being dropped, right? What would it be? Let's try it out. The correct answer would be A. Acceleration and velocity would both be down. They would not be up because it's, first of all, it's not moving up, and acceleration is never going to be up. Fun fact, acceleration will always be down. That's a really nice thing to latch on to. There's nothing that changes that feature at all, which is really helpful. But you have to pay attention to the motion for velocity. And again, in this case, we're moving down. Okay. So in the next video, I'm now going to basically do more kinematic equations. Quite honestly, that's all I'm going to do. I'm not adding new equations to solve this. But what it means is because we're undergoing constant acceleration, we could use those kinematic equations. But the interesting thing about it is that they don't give us the acceleration. They assume, literally assume, that you know it's in free fall. So you have to look for free fall keywords. Is the object being dropped? Is the object falling? Has it been thrown? Up or down? Our problems are going to look empty in free fall. They literally look like nothing's happening. They don't give us all the numbers. But two important features. One, these are solvable problems, despite what you might feel sometimes. And they're tricky. Some problems absolutely trick me still. So don't get discouraged if they're tricky. They are tricky. That's the whole point. I mean, I majored in solving tricky problems. I just like it. I think they're fun. I think they make me very stubborn though, because if I don't get it, I have to spend hours solving it. But anyway, they're tricky, so don't get discouraged if you don't get it right the first time. And I highly recommend totally the trick of, if you're getting frustrated with the question, walk away. Take a break, do something else, come back, start over. It really helps. I do that for playing my piano back here when I'm like playing a piece and I just like, you ever see the cartoons where your fingers get all jumbled up because like you're just like, walk away. It's a really helpful technique. Just clearing your mind really helps. You have time to do that. So if you get stuck on a question or two, you have a day or two to fix that, you know. I think I wanted to make 2 points and I don't remember. So, good enough. Okay, so try again if they're tricky. They are supposed to be tricky. I think that was my 2 points. Yes, and then this tiny little thing warrants way more attention. Yes, we have to model the motion. It's so important. So your problem will be totally wrong if you say acceleration is 9.81. Then you're saying the object is going to get faster as it rises, which doesn't work. So very important you use signs. And that includes the motion up and down, all this stuff. So very, 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 very important. Oh, excuse me. Like that. So we're going to solve in the next video about the Empire State Building. Is the penny drop from the Empire State Building lethal? You know, how fast is it going? Ignoring air resistance. These are real values, so we'll answer that question once and for all. Then we're going to, as always, I like to start small and get more complicated, right? So this one's a pretty straightforward one. This is what I call a plug and chug. This is not a plug and chug. It's a multiple motion question. Same thing. Actually, these are pretty much identical. So they're not identical, I lied. But anyway, the point is that we have multiple motions. This one is identical to that one now that I look at it. This one, so I just want to reiterate. Number 1, plug and chug. Number 2, 3, 4, and 5 are not plug and chugs. But I'll show you how to solve these in the next video and what to do to solve questions that are not plug and chugs. Okay? All right, I'll see you in the next video.